We're going to be talking about the first derivative test, and this is the meat, the big kahuna of notes with chapter 4. So I'm not going to talk too much here at the beginning, but just know this is a little bit long, so you might want to take breaks, pause a little bit as you're working through these. Okay, so to start out, we're going to be kind of analyzing our graph and talking about how the first derivative, our f prime, can tell us about our f graph. So a function is blank if as x moves to the right, its graph moves up. Okay, so let's just think about this in general. So as x moves to the right, so as we go from the left to right on our graph, the value of our graph is going up. We would say that function would be increasing. Okay, so that is the official math term. An increasing function is one that goes up as we go from the left to the right. A function is blank if, as x moves to the right, its graph moves down. Just the opposite of increasing, it would be decreasing. Okay, and a function is blank on interval if it is either increasing or decreasing on the entire interval. Now, this is a fun little vocab word, but not super huge, but it is known as monotonic. Okay, which basically means it's only ever increasing or only ever decreasing. Okay, so over to the left and the right, okay, let's say this is f of x. Okay, we want to identify our areas where f of x is increasing and our areas where f of x is decreasing. So let's go ahead and say increasing is going to be this little green highlight, and decreasing is going to be our blue highlight. So it is increasing here in this first little interval up to about 4, and then that would be decreasing in the middle. So then right here starts increasing again, and then here in the middle we are decreasing, okay, from about 0 to probably about 2.5. Okay, what I want you to notice, okay, is the specific points where it switches between increasing or decreasing. Okay, and it's occurring, not that. Okay, that switch is happening at relative maxes or relative mins, or what we know to be critical points, or what we know is the derivative equaling 0. It has that horizontal tangent line. So last class we talked about extrema and how we can use critical numbers to locate extrema. Well, not only can we use them to locate extrema, like maxes or mins, we can also use those critical numbers to locate when my f of x graph is switching between increasing and decreasing intervals. Okay, so to actually find those increasing and decreasing intervals, we're going to find the critical numbers by setting our derivative equal to 0, and then we're going to set up test intervals. So just like here on this graph, think about it as wherever I have a critical number, that's going to create an interval. So between negative infinity to 0, 0 to about 2.5, and then 2.5 to infinity. Saying I didn't have that graph, those would be my test intervals for this function. Then we're going to determine the sign of f prime at one test value in each of the intervals. And then we're going to use our what we know about increasing and decreasing, which we're going to talk about here in a little bit, to determine, once we know the sign, if that tells us it's going to be increasing or if it's going to be decreasing. Hey, so theorem 3.5, which don't worry about the number. Really, it's just the test for increasing and decreasing functions. If our first derivative is greater than 0, which if the first derivative is greater than 0, then that means the first derivative is positive on the interval, then f is increasing. So if the first derivative is positive, then f is increasing on that same interval. Okay. If f prime is less than 0, on that interval, which means it's negative, then f is decreasing on the interval a to b. So negative, decreasing, positive, increasing. And then last but not least, if f prime of x equals 0, it's constant because it's a critical number. So we're having that slope of 0 occurring, which is why we talk about it as constant. So let's actually put this into practice. Let's look at number 1. So we want to find the open intervals on which f of x is equal to 2x squared minus 4x plus 1 is increasing or decreasing. So first and foremost, I'm going to find my derivative. So f prime of x is equal to 4x minus 4. Then I'm going to set my derivative equal to 0. So 0 is equal to 4x minus 4, which means 4 is equal to 4x, which means x is equal to 1. So found my derivative, set my derivative equal to 0, solved for x. This is my critical number. X is equal to 1. So that means it's this point on my graph where I could have a relative max, a relative min, or just be a critical number, which means I'm going to have should have some sort of switch probably happening there. Might not, but should. Right? So then, remember we said we're going to set up test intervals. So over here, just like a number line, we're going to stick 1 on the number line. Okay? And to the left and the right are going to be my intervals of 1. Okay? And this is just some notation that I think is going to help you keep all this information kind of straight in your brain. Okay, so on a number line, we want to denote the top is going to be what's happening on f prime. The bottom is going to be what that means for f. Okay, so now I need to plug in numbers on my test intervals. So my interval is values greater than 1 and values less than 1. So a value less than 1, make it easy. I could do f of 0. And a value greater than 1, make it easy. I could do 2. Okay, so now I'm plugging these into f prime because I want to know the sign on f prime, not on f. Okay, so f prime of 0, I go to my function. 0 times 4 is 0. 0 minus 4 would be negative 4. F prime of 2, 2 times 4 would be 8. 8 minus 4 would be positive 4. So for my interval less than 1, I got a negative value. For my interval greater than 1, I got a positive value. Now, what we just talked about in our theorem for increasing and decreasing, if my derivative is greater than 0, then f would be increasing. So greater than 0, I'm going to draw that little upward going arrow to denote increasing values. F prime is less than 0, then f is decreasing. So here where I'm negative, that's less than 0. So I'm going to denote the little downward arrow for decreasing. Okay. So now what do? For my answer, I'm just going to state where it's increasing or decreasing. So by this information, therefore, I would say f is increasing on the interval 1 to infinity. And I'd say that f is decreasing on the interval negative infinity to 1. And that's it. Okay, so every time we want to find intervals of increasing and decrease, okay, we take the first derivative, we set the first derivative equal to 0, we find the x values of the critical numbers, okay, which is where the first derivative equals to 0. We put those on a number line to set up our test intervals. We pull numbers from our test intervals and plug them into the first derivative because I want to know the sign of the first derivative. And then once I know the sign of each of my test intervals, I use that to determine where my original function f is increasing or decreasing based upon my theorem of increasing and decreasing. Not too terrible, yeah? Let's do another example. So number 2, find the open intervals on which f of x is equal to x cubed minus 3/2 x squared is increasing or decreasing. So once again, derivative first. So f prime of x is equal to 3x squared minus 3x. Okay, 2 would come down, 2 and half would cancel out. So then set our derivative equal to 0. So 0 is equal to 3x squared minus 3x. Factor out of 3x. 0 is equal to 3x x minus 1. So we get as our values for x is equal to 0 and 1. So then once again, we set up our number line. But now we have 0 and 1. Okay, f prime on top, f on bottom. So once again, I still want to know the signs of f prime to tell me about what's happening on f. So f prime of value less than 0, we could do negative 1. F prime of value in between 0 and 1. Okay, really, I think the easiest number is 1/2. You can pick anything, though, in between 0 and 1. And then f prime of something bigger than 1. So just 2 would be pretty easy. Okay. I don't want to take up your time too much on these notes with plugging in numbers, so I'm going to let you plug these in real quick, pause me, and then start me up again. All right, you should have gotten 6, -3/4, and 6 for plugging in your values. So that gives us positive, negative, positive on our intervals, which means increasing, decreasing, increasing. Okay, so now we just need to write our answers. So therefore, f is decreasing on the interval 0 to 1. 0 to 1. And we are increasing. So now we have multiple increasing intervals. So we're going to have to use our union sign. So -infinity to 0 in union with, which is a capital U, 1 to infinity. Okay, and you should recognize that from pre-calculus. And there we go. That is our answer for number 2. Okay, so now let's take it up a notch because we can find increasing and decreasing intervals, but there's another piece of information we can actually tell from the same work we've already done. So no extra work, okay, but we can gander another piece of information from this. So we can use the first derivative test to tell if my critical numbers that we find are going to be relative maximums or relative minimums. Now remember last class with extrema, we plugged into the original function to find out if something was an absolute max or an absolute min, but we didn't do anything with relatives. Okay. Well, now we're going to take our critical numbers and we're actually going to determine if they are a relative max or relative min, or if they're neither. Okay. So our 3 cases that we could have is if f prime changes from a negative to a positive, then f has a relative minimum. Okay. So if I'm going from a negative value to a positive value, then that means I have a relative minimum at that critical number. If f prime changes from a positive to a negative, then f has a relative maximum, okay, at that number. So negative to positive on f prime is a minimum. Positive to negative on f prime is a maximum. And then last but not least, if we do not have a sign change, so if I go positive, positive, or negative, negative, which can happen, hasn't happened yet, but can happen, okay, then it's neither a relative minimum or a relative maximum. It's just a critical number. Okay, so let's envision this a little bit, because right now I'm just saying stuff and you're like, Mr. Arbone, how am I ever going to keep those straight? So let's look over here at our picture, our graph. So f prime changes from negative to positive. So if f prime is changing from negative to positive, then that means f is going from decreasing to increasing, because that's what negative and positive on f prime means. So look over at our graph, where our graph goes from decreasing values to increasing values. What do we have down there at the bottom? We have a relative minimum. Okay, so that's why we know that to be true. Vice versa, if f prime changes from positive to negative, then that means we're going from increasing to decreasing on f. So when we go from increasing to decreasing, we're going up, and then we have to turn back around and head back down. So that's how we get that relative max being formed. And then, of course, if I don't have any change, that's how I have that neither minimum. An example of this would be like if I had my nice little cubic function and say I like flattened out and then just kept going up, then right here in the middle, even though there might be a spot, and you know, pardon Mr. Arbone's bad drawing skills, where the tangent line might be 0. Okay, I didn't actually switch directions. I didn't go from increasing to decreasing or decreasing or to increasing. So because I didn't switch, I don't actually have a relative maximum or a minimum. Okay, hopefully that makes sense. This goes for number 3. Okay, so example number 3. Let's actually put this into practice. We want to find the relative extrema of the function f of x is equal to 1/2 x minus sine x and the interval 0 to 2 pi. Okay, so first and foremost, just like we've done before, we're going to take our derivative. So f prime of x, f prime of x is equal to 1/2 x would just become 1/2. Minus sine of x will become minus cosine of x. Then I'm going to set that equal to 0. So 0 is equal to 1/2 minus cosine of x, which means I want to know where cosine of x is equal to 1/2, and where between 0 and 2 pi is cosine equal to 1/2. That would be at pi over 3 and 5 pi over 3. 5 pi over 3, and pi over 3. Okay, and that's just from the unit circle, working backwards. Remember, trig is a thing too. Even though we don't like trig, we do still have to work with trig. Okay, so now just like before, we're going to set up our number line. So f prime f pi over 3, because it would come first. Then 5 pi over 3. Okay, and just like before, I'm going to pick numbers on my number line. On my test intervals. Okay, now you might be like, Mr. Arbone, how am I going to pick numbers with trig? I don't even know the unit circle that well. Okay, pick easy numbers when you're dealing with trig. Okay, what are our easiest numbers to plug in? 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, your quadrantal angles where it's just going to be 0 or 1, that's going to be the easiest. Make your life easy. You get to pick any number on this interval. Make your life easy. So what's a number in between pi over 3 and I don't want to go negative infinity, but, you know, if we kept going, remember how our trig functions are cyclical. They repeat over and over and over again. I'm not going to hit another critical number until another pi over 3. So it would be like negative pi over 3 and so on. Okay. So I can use 0, even though 0 isn't technically included in our interval, because I know nothing should happen on my function until I get to another pi over 3. Okay, so I'm going to choose f prime of 0 for my first one. Okay, and if you're confused on that, y'all, please feel free to ask me in class. Okay, in between pi over 3 and 5 pi over 3, you got a couple options. You could do pi over 2, you could do pi, you could do 3 pi over 2. You got lots of them. I think pi is the easiest, so we'll do f prime of pi. And then in between 5 pi over 3, and we don't want to go too far, so I would say 2 pi. Just do the same thing as we did in 0, and the nice thing, whatever it is at 0, it's the same thing at 2 pi. So you're really only having to solve for 1. Okay, and you can pick slightly different things, y'all, as long as they're in your intervals, but go ahead and pause me again so you can solve these out. All right, y'all, hopefully you got -1/2, 3/2, and -1/2. So we can add that information up onto our number line. So negative, positive, and then negative, which means we are decreasing, increasing, and decreasing. Okay, so we want to find the relative extrema. So now we're going to classify. So x equals pi over 3 is our first critical number. And using our test at x equals pi over 3, we went from negative to positive. So looking up here, negative to positive, it's a relative minimum. Okay, our other one, x equals 5 pi over 3. We went from positive to negative. Once again, using our first derivative test, positive to negative is a relative maximum. And I do want to point out, y'all, okay, see on our little number line here, how it kind of creates almost a shape of the graph. So you can see here where I go from decreasing to increasing. If you just follow the arrows, it makes that shape of a relative minimum. If I go from increasing to decreasing, it makes that shape of a relative maximum. So that's why we use this work, because it actually helps you remember the first derivative test. It helps you remember this information. Okay, and that would be our answer for classifying our extrema. All right, for 4 and 5, I don't want to make this notes video too long, so I'm going to let you practice it, okay? Go ahead and pause me here, and then I'm going to pop over and I'll just go over the information for each of them. But go ahead and pause me, and then you can unpause me if you need to, get a little help, and then go back and check your work, okay? All right, y'all, go ahead and check your work. I'll give you a few kind of seconds to look over this while I'm talking through it. So our derivative for 4, we get 2/3 x squared minus 4 to the negative 1/3 times 2x. Okay, it is a chain rule. Simplified a bit, you get 4x over 3 times x squared minus 4 to the 1/3. Then when I'm finding my critical numbers, remember critical numbers come from where the function is equal to 0 and when the function is undefined. So anytime your derivative is a fraction and you're looking for critical numbers, you should just set both the top and the bottom of the function equal to 0, because the top is going to be where the function is equal to 0. The bottom is going to be where the function is undefined, both of which give us critical numbers. So just go ahead and do and take care of both. So we get 0 equals 4x, x equals 0, 0 equals x squared minus 4, x equals positive or negative 2. So setting up our number line with negative 2, 0, and 2, my test numbers I picked were negative 3, negative 1, 1, and 3, giving us negative, positive, negative, positive. So we go decreasing, increasing, decreasing, increasing, which gives us relative mins at negative 2 and 2, and relative max at 0. Okay. Number 5, you could have done this by simplifying first, or you could have done this by quotient rule. But either way, you're going to have to simplify before you can solve for those critical numbers. So your simplified function should still be 2x to the fourth minus 2 over x cubed. So if you're struggling with that derivative, once again, ask me in class, and I can go through that with you. So set the top equal to 0, 0 equals 2x to the fourth minus 2. Set the bottom equal to 0, 0 equals x cubed. So we get x equals 0 and x equals positive or negative 1. So put negative 1, 0, and 1 on our number line. The numbers I chose, negative 2, negative 1/2, and 2 for my test intervals. And those should all be f prime. Sometimes I forget to add an extra prime, and I don't want to confuse y'all. So once again, we're always plugging into the first derivative. What I want to know about the sign of first derivative. So negative, positive, once again, gives us relative max at 0 and relative mins at negative 1 and 1. I just drew in those little curves so you can kind of see. Obviously, that's not exactly what the function looks like, but it's kind of a rough idea of how it would flow based on the increasing and decreasing information we have. Okay, let's keep going, y'all. Okay, so number 6, we want to use the graph of f prime to identify the intervals on which f is increasing or decreasing and estimate the values of x at which f of x has a relative maximum or minimum. Okay, so I have given you the graph of f prime in number 6. Okay, so if this is f prime, we're going to use this information to tell when f is increasing or decreasing. So f increasing or decreasing. Okay, so remember, when f prime is positive, f is increasing. So f prime is positive from about negative 1 to 1 and about a little less than 4, but onward. So where f prime is positive, f is increasing. So it's a little weird to think about. It's almost like you're thinking backwards. Okay, but our intervals would be, and we're going to go estimate, so don't think these are the exact numbers, obviously, but negative 1 to 1 in union with 4 to infinity. Okay, when f prime is negative, f is decreasing. So looking at my graph again, negative means below the x-axis, so here and here. So those intervals would be negative infinity to negative 1, roughly, in union with 1 to 4. Okay, so you're kind of thinking backwards. Okay, then estimate the values of x at which f of x has a relative maximum or minimum. So know that our max and mins occur at critical numbers. Critical numbers occur when the derivative is equal to 0. So my critical numbers are going to be right here where my derivative is equal to 0. So essentially when my derivative crosses the x-axis, those are my critical numbers. Okay, so my critical numbers are, we'll go with those same estimates, negative 1, 1, and 4. And now let's classify them. At negative 1 and at 4, we're going from negative to positive. So remember, going from negative to a positive, going back to our theorems, okay, is a relative minimum. So both negative 1 and 4 would be relative minimums. And then at 1, we're going positive to negative, so that would just be the opposite, a relative maximum. Okay, so that's kind of the same information, but now we're looking at it graphically instead of algebraically, and we're kind of working backwards. I've given you f prime instead of f, and you have to go tell me about f, having f prime. So it's weird to think backwards, right? But it'll take some getting used to, but we do it a lot. Okay. So the next thing we're going to talk about in terms of identifying features of our graph is concavity. Okay. Concavity has to do with the shape of the graph. So increasing and decreasing has to do with like going up or going down. Concavity has to do with the shape. Okay. So let f be differentiable on an open interval I if the graph of f of x is concave up on the interval I, then the graph of f of x lies above all of its tangent lines on I. So what that means, okay, over here on the right, okay, your concave up sections are the red sections. Okay, so over here on the right, I want you to look, those concave ups. Okay, so a couple things about concave up. Concave up forms a U. Okay, so see how it forms that U shape? Okay, so that's one way to help identify concave up. And then what it means by it lies above all of its tangent lines, if I were to draw tangent lines at any point on a concave up curve, the curve of my function would always rest above its tangent lines because all of its tangent lines would fall below the graph. Okay, so that's what it means by it lies above. But realistically, just think concave up is that U shape. It's that upward U. Okay, it opens up. Let f be differentiable on an open interval I if the graph of f is concave down. So this is just our opposite shape, concave down. On I, then the graph of f of x lies below all of its tangent lines on I. So our concave down sections are our blue sections on the graph. Okay, notice how concave down, okay, it just is the exact opposite of concave up. It forms kind of that upside down U. Okay, so instead of upwards U, upside down U. I don't want to say N because N doesn't really connect to anything. Okay, but concave down. And once again, if I drew tangent lines at any points, the graph would be below the tangent lines. That's what makes it distinctively concave down. Don't know what happened, y'all. Just ignore that screen that popped up for like 2 seconds. Okay. So now let's actually talk about how we can find concavity. Okay. So to determine concavity, we're going to locate the points where the second derivative is equal to 0 or does not exist. So kind of the same idea we did for critical numbers, where we work with the first derivative equaling 0. We want to work with the second derivative. Okay, these spots where the second derivative is 0 or does not exist, we call these possible points of inflection, or PPOI for short, which doesn't feel short, but it is. Okay, then just like we did before, the process is exactly the same, except we're working with the second derivative. So use those x values to set up test intervals, test the sign. If we are greater than 0, so positive, then we're concave up. If we are less than 0, so negative, then we are concave down. Okay, and a point of inflection, so we said they were possible points of inflection. An actual point of inflection is if we have any sort of concavity change. So a point of inflection is if the concavity changes from upward to downward or downward to upward. So we don't have to get picky with positive, negative, negative, positive. It's just any sign change on the second derivative and your possible point of inflection becomes an actual point of inflection. Okay, so we're going to look at number 1. Given y is equal to negative x cubed plus 3x squared minus 2, we're going to find all increasing and decreasing intervals, all relative extrema, all concavity intervals, and all points of inflection. So we're going to do all of it for this one function. So much information. Okay, the biggest thing is just to keep your derivative straight and make sure you're plugging into the right function. So First and foremost, we need to find our first derivative. So f prime of x would be equal to negative 3x squared plus 6x. Negative 2 would go away. Then we can find our second derivative, which would be negative 6x plus 6. Okay, then we're going to set our first derivative equal to 0. So 0 is equal to negative 3x squared plus 6x. Factor out a 3 and an x. We get 0 is equal to 3x. See, negative x plus 2. So that would give you x equals 0 and 2. Okay. Then our other one, negative 6x plus 6, we're also going to set that equal to 0. So 0 is equal to negative 6x plus 6, which gives us 6x equals 6, which gives us x is equal to 1 by dividing those 6's out. Okay, so 0 and 2 came from the first derivative, which means they are critical numbers. 1 came from the second derivative, which means it's a possible point of inflection. It's important that you keep those straight. Okay, so whatever order you want to do this math to make sure you don't get those things mixed up, that's what you need to do. Okay, so let's set up our number lines for both. So number line here, which should look familiar for f prime, we're going to have 0 and 2, f prime on top, f on bottom. And then I'm going to set up another number line for my second derivative. So f double prime, f on bottom, and then I only have 1. So notice I'm not putting all the points on each. I'm only putting the possible point of inflection with my second derivative because it comes from the second derivative. I'm only putting my critical numbers on the first derivative because it comes from the first derivative. Okay, now once again, we're going to pick numbers for everything. So my numbers on my intervals, we would do f prime of negative 1, f prime of 1, and f prime of 3. Remember, you can pick anything as long as it falls in the intervals. I just usually pick what I think is the easiest. And then for my second derivative, we would do f double prime of 0 and f double prime of 2. And you can pause me again, y'all, so you can do that math real quick. All right, so you should have got negative 9, 3, and negative 9. So that's negative, positive, negative on our first derivative, which means decreasing, increasing, decreasing in our shape of our graph. Then we get 6 and negative 6 on the second derivative. So positive, then negative, which means concave up and concave down. So I draw the shape of the concavity on my second derivative, which makes it even easier to remember. Okay, so we have all the things we need. Now we are going to list out all of our information. Okay, so part A, we are increasing because we're doing increasing, decreasing. So we're increasing on the interval 0 to 2. We are decreasing on the interval negative infinity to 0, 2 to infinity. And union with 2 to infinity. Okay, part B, relative extrema. So 0, we go from negative to positive, so that's our relative minimum. Okay, at 2, we go from positive to negative, so that's a relative maximum. Okay, C, concavity. We are concave up where we're positive, so negative infinity to 1. We are concave down when we are negative, so 1 to infinity. And then last but not least, part D, points of inflection. We got 1 right at 1 because we changed signs, positive to negative. Doesn't matter which way we go. Okay, but x equals 1 is a POI, a point of inflection. All right, y'all, and that's a full everything. You did all the things for this graph. We know all of the information, all the important details. We could basically graph it at this point, which we will do eventually when we do curve sketching. So get excited. Okay, moving on to the back page, y'all. Okay, I'm just going to pause and then show you all the answers for these. For 3 and 4, they're really just kind of some practice problems for you. Or sorry, 3 and 2. for you to keep getting some more work with this. We're going to do lots and lots of practice in class, so I don't want you to freak out if you're like, Mr. Arbone, that was so much. I just don't want to make these notes too much longer because we're already going on 35 minutes. So pause me real quick, and then I'll spend the last couple minutes going over 3 and 2, and then we will be done. All right, y'all, if you powered through and finished out these notes, you're probably really upset with me because you're like, Mr. Arbone, those 2 questions were a lot. And you're correct. Those were a lot. But let's talk through them real quick because there's some important things we get in all of them, which is why I wanted to do them. So number 3, first derivative, 4x cubed minus 12x squared. Second derivative, 12x squared minus 24x. Set both equal to 0. We get 0 and 3 as critical numbers and 2 and 0 as points of inflections. Remember, y'all, just pause me if you need to copy stuff down, and then you can listen to my explanation. So then choosing my test intervals over here to the right, -1, 1, and 4 on the first derivative, -1, 1, and 3 on the second derivative. One thing I want you to notice, we got the same number as a critical number and as a possible point of inflection. Anytime that happens, that just means that number is going to be either a relative extrema or a point of inflection. It can't be both. It can't be both a maximum and a point where concavity changes. Because think about that. If I have this nice little bump, my concavity can't change there because the whole bump is concave down. Okay, so if you get the same number for a critical number and a possible point of inflection, just know it's only going to be one or the other. So on f prime, we get negative, negative, positive for decreasing, decreasing, increasing. On f double prime, we get positive, negative, positive for concave up, concave down, concave up on f, which gives us our important information. So we see here that at 0, we did not have a sign change on the first derivative. So 0 was not relative max or minimum. We did have a sign change on the second derivative, so 0 was a point of inflection. So that's what I mean by it can only be one or the other. Okay, and then all of the answers are over there to the right. I'm not going to go through all of them because hopefully you can read my work. All right, number 2, this one was a doozy just because its derivative was kind of a mess to have to derive and then also actually do something with it. If I didn't have to do something with it, it would have been a much easier derivative, but I wanted to do something with it. So I want to know when it's concave up or concave down. So I have to take not just the first, but the second. So take the first derivative, simplify it down as much as I can. Take the second derivative, simplify it down as much as I can. And you should get 30x squared plus 40 over x squared minus 4 to the third. And, you know, this is what I meant in chapter 3, where it's like you don't have to simplify things, but sometimes you're going to have to simplify your derivatives because you want to do something with them. So this is that time where now it's like you need to be able to simplify your derivatives so you can do things with them. So 30x squared plus 40 over x squared minus 4 cubed, rational function. So once again, I'm going to set both the top and the bottom equal to 0. When I set the top equal to 0, though, I get x is equal to the square root of negative 40 over 30. So I can't take the square root of a negative number. That would be an imaginary or a complex number, which don't show up in the normal plane. You should have talked about that a little bit in Algebra 2 and pre-calculus. So we're not going to worry about it. We're not dealing with complex calculus. You'll deal with that maybe in college one day if you decide to study math like the awesome people. Okay, but don't worry about it for now. So if you get an imaginary or complex answer, it's not a critical number or point of inflection. And then our second one, we get 0 is equal to x squared minus 4, which gives us 4 is equal to x squared. So we get x is equal to positive, negative 2. Much easier on the second one. Then we get our test intervals, positive, negative, positive, concave up, concave down, concave up, and we come to our conclusions. Right, y'all, that concludes possibly the longest notes of the year. Don't hate me, okay? We will go over this all again in class. If you have any questions, please do not hesitate to ask or reach out. I know this is a lot of information. It just is better to do it all in one sitting than to try and split this up over multiple days. But anyways, thank you for tuning in. Make sure you complete your notes if you didn't complete your notes.